BMO Round 2, 2019 British Mathematical Olympiad problem number 2. If you want to solve this problem, if you want to know and we want to work on background idea, this problem needs an idea that is useful for many other problems in BMO Round 1 and Round 2 and also other exams, AMC for American Mathematics Competition and USAMO for USA Mathematical Olympiad. If you want to learn other ideas and also want to know the solutions of other problems of BMO Round 2, as I said before, feel free to send a message to my WhatsApp number in the description and comments. Okay, so let's read the problem. For some integer n, a set of n squared magical chess pieces arrange themselves on a square n squared by n squared chessboard composed of n to the 4 unit squares. At a signal, the chess pieces all teleport to another square of the chessboard such that the distance between the centers of their old and new square is n. So this part is important. The distance between the old and new square is n. The chess pieces win if both before and after the signal there are no two chess pieces in the same row or column. For which values of n can the chess pieces win? Okay, so when we see this problem, at first pause the video and try this problem on your own. If you couldn't, let's do it together. For this problem, when you can't solve a problem and nothing comes to your mind, what's the most useful idea? I can say it's the most useful idea in BMO, in USAMO, in IMO, also in easier parts like AMC, AME, BMO Round 1 is what? And here we can use it. The idea is considering a small example. So we should consider a small example and try to not find only pattern. Try to generalize the idea for general n. So let's consider small examples. Now here, and in many problems, for example, maybe more, for example, we have two variables, or for example, maybe we have three things. We should see that we should use small example on what? Here, the only variable is n, so let's start to use a small example on n. First, n is 1. Is it possible? So it is 1 by 1. We have one chess piece. If we want to move it, the distance from here between the centers of this one of its old and new square is n, is 1. It's not possible because we cannot move it. For n2, sorry. It is 1 squared, it is okay here. But for 2 and n is 2, our square is 2 squared times 2 squared. So it is 4 by 4. So let's draw. Okay. We have this. And let's draw the lines here, 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 here. Now we have 4 pieces. So the initial case, one useful way, let's copy this one first. Okay, because we want to use it again. Maybe. So if you have something like this, okay. So look, the distance here can be vertical or horizontal, or if it want to be oblique, so the distance is 2. So here x and y should be integers. So x squared plus y squared is 4. Okay, so because x squared plus y squared is 4, by Pythagorean theorem, we can see that it is not possible because if x is, for example, if it is oblique, means if it is 1, it will be 3, which is bad. If it is 2, 2 squared, which is 4, it will be 0. So it is, if 0, 4, 4, 0, they are vertical and horizontal, and we don't have any oblique case. Now, let's move it. For example, I move this one here 1, 2 units to right. This one 1, 2 units to right again. This one 2 units to left. This one 2 units to left. And we will see if we consider black cells, the new places, they are in different rows and different columns. So we will see N2 is okay. Okay. Now from here, I want to say I guess that N2 possible like this and even numbers are possible. Okay. So let's first check, for example, N4, and after that we want to generalize it. For N4, let's do something. We should have a table with 16 rows and 16 columns. Okay. Okay, here N is 4 and it is a 16 by 16 table. So let's see for N2, which was 4 by 4, we consider the initial case, main diagonal. So here I draw this one, this one, this one, the main diagonal. And after that, we want to move them like case n equal to 2. In this case, the distance was 2. In this case, the distance is n. The distance is 4. Okay? So let's see. If the distance is 4, so let's move it 1, 2, 3, 4. It is 4. The next one, 1, 2, 3, 4. Next one, 1, 2, 3, 4. Let's see. 1, 2, 3. And also look, we should move one of them to left to not miss this column, because in every column we should have chess piece. So 1, 2, 3. This one 1, 2, 3, 4. So for this one we move it here, and this one 1, 2, 3, 4. Okay. And this one we move it here, move here, move here. Then we don't move this part because it will be like they will be in same column, these two things. Okay, so after this part, we've filled, let's draw this one and this one. It is what? 1, 2, 3, 4, 5, 6, 7, 8. We've, this 8 by 8 now is okay. So if we do the same thing for next 8 by 8, 1, 2, 3, 4. Okay, next one this, next one this, next one this, and for this one, 1, 2, 3, 4. This one we will see, okay, that's good. And all in second case, in all rows and all columns, we have only one chess piece. So now we want to generalize it for any even number. So let's consider n is equal to 2q, and let me tell you, when you want to write in your answer sheet, you don't need to write these things. You say, okay, our claim is for n2k, it is okay. So our square is 4k squared by 4k squared. So let's draw a table by this property. Okay, so here you say I move the first one 2q plus 1. So if it is in 1, if you move with 2k to the right, so it will be 1. Let's see, 2 is 1 more, so it will be 2k plus 1. Okay, the next one is 2, you move it to 2k plus 2. Okay, and then you move it up to which part? If you consider for 2k, we move it to what? 2. 2k plus 2k, which will be 4k. And now, next one, it is in 2k plus 1, you move it to left to first column. And again, you move the next one and next one up to, let's see here. Okay, if you want to find 2k plus 2 goes to 2. And we want to see up to this part, the number of pieces here should be equal to here. So here, how many we had? 2k. So 2k plus 1 to 4k. If it comes to 4k, we move it to what? We move 4k minus 2k to 2k. Okay, to this part. Now, in this part, let's see what rows and what columns are okay. So as you can see, This 4k by 4k will be correct in every rows and in every columns. In second initial case and second case, there is exactly one piece. So we know that the size is what 4k squared to 4k squared. So how many squares like this are there? You say 4k squared over 4k, which is k. So we have k squares like this. It was the first one. Then we have second one. We correct the next square exactly like this, and we continue up to last square. And last square, it will be what? It will be kth square, okay? So it will be kth one. And okay, we can correct all these things exactly with a similar way, exactly like this. You move the first k pieces n units to the right, and let's say first 2k pieces 2k units to the right, next 2k pieces 2k units to the left. Okay, so 2k's are good. We can say it is our first part. Let's consider lemma 1. Now let's focus on odd parts. For n1 we saw that it is not possible. Now let's check n3. For example, for n3 we need a 9 by 9 table. Okay, let's draw. Okay, here let's check again. For example, see, can we find a good example for 9 by 9 and 3? For example, if we move 1, 2, 3 units here, the next one here, then this one here, for this one we move it here, we move this one here, we move this one here. And for these 3 by 3, it's not possible. You should move them only in this part because other rows and columns have been filled like this. It is not possible, but maybe our example is not good. We can check many different examples. For example, 1, 2, 3 units here, and 1, 2, 3 units here, and something like this. And if you check a lot of examples, you would see it seems to be not possible, but it is not enough. We should prove, we should find a way. When you want to prove something is not possible, you should use invariant, okay? And in invariant, we have lots of things. Parity, divisibility or remainder by a number, and the other one is, for example, some functions. The other one, especially when we have a figure, for example, like here, 9 by 9, coloring. And in coloring, we have three main colorings: column coloring, checkerboard scheme, general form of checkerboard scheme, type 1, type 2. And the most important one is checkerboard scheme coloring. Many problems of BMO can be solved with these. I can say you can solve 95% of the problems related to coloring by these three ideas, but here we have two types, 2, 1, 2, 2. If you want to learn important ideas in invariant, especially it was useful in SUMAC, Stanford, a summer camp that is prestigious, and if you apply for SUMAC, it is so much good for your CV. In that problem, there are in that it's not exam. They release some problems, around 8 problems, and you have around 2 weeks, 3 weeks to work on them, and you send your solution. And if all your solutions are correct and your CV is okay, they accept you, and it will be a good thing, so much good thing for your CV, distinguishable property. And in that problem, in those problems, we have lots of invariant problems. Okay, so if you want to learn invariant problems, for example, graph permutation, lots of things, you can send message to my WhatsApp number. Let's work on checkerboard. Here, I color these cells black and white alternatively, and why it is important. Now here, we know n is odd, and when we move a piece from an initial square to the new square, what are the colors of the initial one, old square, old place, and the new place? So pause the video and try to see what can we say about the color of old square of a piece and new square of a piece. So let's check them. This one is black, black, like this one and this one. Okay. So let's see on this figure what happens. Okay, if we move, for example, 3 units to right. So let's move this, select this one. 1, 2, 3. So if we move 3 units horizontally, 1, 2, 3, or also to left and right, the colors will change. It is black, the color of the new squares are white. If we move vertical, again, it will be white. And this one will be white. So I think it's good. But maybe you say, okay, 3 not possible. But for 5, for example, when you move 5, you can move oblique. For example, 3, 4. What happens? So let's also consider this to see, can we say that always the color of old square and new square of a piece the colors are different? Can we say that? So let's check. Suppose if it is oblique or vertical or horizontal. So it is what? Suppose n, and we know n is odd. So it is, if it is horizontal, you say, okay, first one, second one, third one, okay, 1 unit to the left, right, 2 units to the right. So as you can see, when there is n units to the right, it will be n plus 1. And for example, without lots of generality, suppose first one is black. So first one, third one is black, n plus 1 is even. Okay, because n is odd, we are considering the cases that n is odd. So n is odd, so it will be black, it will be white. So the old square is black. When we move it to new square, it is white. So we prove this part. This one vertically is same. And look, if we move to left or right, the colors are different. It's not important left to right or right to left. Here, from top to bottom or vice versa, again, they are same without loss of generality again. It is 1, it is 2, it is 3, it is n, and then first one is black, third one is black, n is odd, nth one is black, and this one is white, so n units to the right, n units to the bottom, n plus 1. Again, the colors are different. Now, the hardest part here. You consider this one. For example, without loss of generality, this one is black. We want to see this one is white or not. So it is n, it is a units here and b units here. So a squared plus b squared equal to n squared. N is odd, so n squared is odd. Now we consider one of them even, a and b, one of them odd, without loss of generality. Suppose it is odd, it is even. So it is the first one, it is second one, because we have a units here, so it will be a plus 1. A plus 1 is what? Because a is odd, a plus 1 even. And then, because it is even, second one white, third one black, this one will be white, okay? And now, here, you say, okay, it is x, for example, this one is x plus 1, because it is b, it will be x plus b. X is white, x plus 1 is black, okay? So because b is even, it is similar to x plus 2. So x plus 2 is white, x plus b is also white. Okay, so here it is black, it is white. So we proved also in an oblique way, in general case, the colors of old square and new square of a piece are different. Okay, so we proved this. Now let's use it to prove for n odd it is impossible. Let's first try to prove it for this case. Okay, now, okay, if you consider initial case, let's color them again. Okay, if you consider initial case, in each row and each column, we have one piece. So we have n squared piece first and n squared piece at the end. Okay. So, and what is the difference of black square and white square in mathematics? Again, it is another idea. You see something and you want to find a formula in mathematics for that. As you can see, if the first one is black, 1, 1, if some of, for example, suppose we have a cell in ith row and j column. If we want to see when it is black, when it is white. ij. It is black if I plus j, look 2 and 1 plus 3, 4, if I plus j is even. If otherwise, it is white. Okay, so let's consider for n squared. You have a table. It is 1 to n squared. It is 1 to n squared. Suppose the old places or old squares are I1, J1 to IN squared and JN squared. Okay? Now suppose new places are I prime 1, J prime 1. When we move it, and I prime n squared and j prime n squared. From the problem, because we know one of them is white, one of them black, we know that I1 plus, for example, IK plus JK, because we had K in the solution, IQ, for example, plus JQ. If we consider it with I prime Q plus J prime Q, they are not same mod 2 because one of them is black, one of them is white. Okay, so we consider mod 2. If you add this to 1, then now they are equal mod 2. Okay, so here what we've used so far, considering a small example, you can summarize them using coloring in invariant and the most useful coloring checkerboard scheme. The next idea, third idea, we've considered black and white in mathematics, sum of the rows and columns, mod 2 important. And now another idea is to add all things. In many problems, if you have many conditions, if you add all of them, most of the time useful. So let's see. If you add I1 plus J1 plus I2 plus J2 to IN squared plus Jn squared, we know that mod 2 it is equal to I prime 1 plus J prime 1 plus 1 plus I prime 2 plus J prime 2 plus 1 up to I prime n squared plus J prime n squared. Let's write prime here plus 1 mod 2. Okay, now left side is what I1 plus, we know in I1, I2, IN squared because in each row we have one piece. So I1, I2, IN squared is a permutation of 1 to n squared. So it will be 1, 2 to n squared. Similarly, we can say for J1, J2 to Jn squared, also it is a permutation of 1 to n squared. For I prime 1 to I prime n squared, we can say same thing, and J prime 1 to J prime n squared. And also we have some ones. How many ones are there here? There are n squared ones, so it will be plus n squared mod 2. Now, in this case, you can say, okay, in mod 2, we can cancel these two things. We can subtract 2 times 1 to 1 squared, 1, 2 to n squared from both sides. So n squared is congruent to 0 mod 2. So it means what? It means that n squared is even. So n is even, but we are considering the cases that n is odd. So that's a contradiction. So we proved. We at first here, the beginning, we considered that it is possible for n odd. We've considered all places, new places. We've considered the colors are different. So IQ plus JQ for the related one, new place of that. I prime Q, J prime Q, they have different parity, one of them odd, one of them even. So if you add one of them to one, add one to one of them, then they are equal mod 2. And then I added all of them, and I saw that, okay, the left side is 2 times this, right side is 2 times this plus n squared mod 2, then we reached that n is even, which is a contradiction. So we proved this problem completely. As I said, if you want to learn important ideas in combinatorics, geometry, algebra, number theory, and want the solution of other BMO round 2 because they've not released the solutions, all solutions of BMO2 yet. If you want to know the solution of this or want to prepare yourself for BMO, USAMO, for Canadian Math Olympiad or other math exams from easiest level to hardest level. As I said before, feel free to send message to our WhatsApp number in the description comments.